Alright, so this first video we're going to be talking about sets and functions, right? So sort of just really preliminary matters for any pure math course, right? But the benefit that we get from doing these three courses in tandem is that we only have to go over the preliminary matters once, right? So the first thing is, this isn't a set theory class, so we're not going to go through defining precisely what a set is, right? We have an intuitive notion of what a set is, and for all of the studies that we're going to do, we're not going to run into any of the sort of counterintuitive paradoxical things that happen in set theory. So we're going to be content with just saying that a set is some collection of distinguishable elements. Right. And once we have defined this object of a set, we can start talking about, how we can relate sets to each other, right? So when is a set equal to another set, right? So this is actually a theorem in the text that we're using, but and it seems kind of silly, right? And it says that A equals B if and only if A is a subset of B and B is a subset of A, right? Now a subset just means that, right, if X is any element of A, so if X is in A, then X is in B, right? That's all this statement is saying. It's just a logical statement relating the elements of A and the elements of B, right? Because we're dealing with sets, which are just collections of elements. So all the properties that we're going to define have to stem from some properties or just statements about the elements of those sets. So again, this seems like sort of a silly thing to denote as a theorem, but it's important because this is the way most of the time that you're going to prove two sets are equal, right? If you have to prove one set is equal to another, then the way you normally go about that is starting in this direction, saying, okay, let's pick any element of the first set, and then I want to argue that it's in the second set, and vice versa, right? So, although this seems really a trivial matter, this is how you prove two sets are equal. The next important thing is the empty set, which is the set containing no elements, right? And you can prove that this is unique, and we denote this by this little symbol. Now, the empty set has a lot of very interesting properties, you could say. One of these being that the empty set is a subset of any set. So this is for any set A, right? And so if we read it like this, we're saying if X is in the empty set, then X is in A, right? But the thing is that here we're saying if X is in the empty set, but there is no X in the empty set. So we sort of start with basically this. This can never happen in a sense. So you sort of say that this is vacuously true, right? Like it has to be true because, in a sense, it can't be false, right? And really this is a matter of almost semantics, right? When you're defining logical operators, right? When you're defining the implication, P implies Q. This is sort of a side note, but P implies Q, right? If you define a logic table for that, right? And part of that logic table is that if P is false, then essentially 0 implies Q is always going to be true. All right, so the next thing is operations on sets, right? So if I have two sets, what can I do with them? There's the union. So what does it mean to have a union of two sets? Well, again, we can define it by looking at the elements, right? What does it mean to be an element of the union? Being an element of the union means you are in A or you're in B, right? Now this or here, again, this is sort of just a side note about logic. A lot of the times in daily usage when we use the word or, we mean it as sort of an exclusive, right? It's either this or that. It could be both, right? We don't really know. But the important thing is that it's not neither, right? One of them has to be true. Both of them could be true, but you can't have both of them being false, right? And then again, that just has to do with the logic table of or, which would be like P or Q. It's like this little V looking thing. The next thing would be the intersection. Right? And to be in the intersection means that you are in A and you are in B, right? So both of these statements must be true at the same time. And I guess I should write if and only if here. This is a double implication. There's also the complement, which has several notations across various texts. So you could write A minus B, you could write A backslash B, or another notation which is like more dependent on like understanding the context is you would write B with a little c superscript, but that's usually when A is, let's say, your entire space that you're looking at, right? This is usually reserved for when you have some clear context of a universal space. Now this backslash notation is fairly common, but I've never really liked it, so I'm going to stick to this notation. So being in A complement B means that you are in A and you are not in B, right? And we can denote sort of not, this is the element sign, right? We can just write a slash through it to denote not in B. And so once you define these operations, there's a lot of things that you can and really should prove, right? Like that this operation is associative, right? It doesn't matter the order in which I take unions, right? So there's a lot of results like that, but we're not really going to spend the time talking about that because, again, it all just comes down to looking at the sets, or really just the elements and the logic, and and really at the end of the day, you could just prove this with an argument with a logic table, and that's not very interesting. The next thing, there are a couple theorems that are very important. One of them, and this is in the text, Sweston, this is going to be Theorem 17, which I just note because my professor would always say it was a very important theorem, and we ended up using it a lot, even though it was like one of the chapter 1 theorems. It was something we always came back to. And it just says that these three statements are equivalent, right? So one is that A subset B. The second one is that X complement B is a subset of X complement A. And the third is that A intersect X minus B is empty, right? So these three are equivalent statements. And so a side note about proving when you have multiple statements that are equivalent, or you want to show that they're equivalent, the typical way in which you prove that is going sort of what we would call cyclic implication. So you would prove that 1 implies 2, and then you would prove that 2 implies 3, and then you would prove 3 implies 1. And this will show, so you would write down 3 proofs, and that would show that these 3 statements are equivalent, right? So as a matter of example, we can show let's just do 1 implies 2, right? So we want to prove that X minus B is a subset of X minus A, given that A is a subset of B, right? So let X be an element of X minus B. So this means, by definition, X is in X, but X is not in B. Now, suppose we can argue by contradiction here. Suppose X is in A, right? Because we want to show it's not in A. Suppose X was in A. Then since A is a subset of B, X is in A implies X is in B, which is a contradiction. Thus, X is not in A, so X is in X minus A, which is what we wanted to prove. Does that make sense?
Yes, sir.
All right. All right. The next thing is the theorem after that, which is De Morgan's laws, which again are essentially just a really just a matter of looking at the logic table. Now, what De Morgan's law says is a relationship between complements and unions and intersections, right? So the first, there's 2 laws, and they're sort of mirror images of each other, right? The first one is that the complement of a union is the intersection of the complements. Similarly, the complement of an intersection is the union of the complements. And again, you would just prove this. You would sort of have 4 mini proofs, right? Because to prove one of these, you have to prove that this is a subset of that, and then that's a subset of that, right? So you have 4 really just statements to look at, and they all just stem from logical tables, right? If X is an element of X minus A union B, then I have to show that X is an X minus A and X is an X minus B. And you really just have to work with the logic there. There's nothing very challenging about it, right? There's no work you have to do. You just have to show that logically it is a true statement. The next topic is families of sets, which they sort of use script letters for that. So what this means is F is a family of sets B sub gamma for each element gamma in big gamma, right? So here gamma is called the index set. And it can be anything, right? We're typically used to index sets like the natural numbers, right? Where we would have sets just B1, B2, and so on, right? Or even just finite subsets of the natural numbers. But the nice thing here is that we can have even just uncountably infinite families of sets, right? So like if gamma was the interval between 0 and 1, we could have B sub 0, we could have B sub 0.1, and really just B sub whatever, right? Just, right? It doesn't really matter. We would have one set for each element in this interval, which is countably infinite, so that's a pretty large array of numbers, and thus a large array of sets. Now for families of sets, we can define sort of unions, or I guess intersections. I wrote intersections first. So here, these are just, a lot of the times you will see a lowercase Greek letter and then the corresponding uppercase letter. So this is this is lambda and lambda. So the intersection of all these sets, again, is just a set, and we can define this set by looking at what it means to be an element of this set. It just means that X is in A sub lambda for every lambda in lambda. Similarly, for the union of a family, sorry, my handwriting is getting sloppy here. X is in A sub lambda for some lambda and lambda, right? So really we could denote this as like lambda 1, right? To drive home the point that this is just, there has to exist a specific lambda 1. It doesn't have to be exactly 1. It could be more than 1. It could be every lambda, but there has to exist at least one specific lambda.
Got that.
And then you can, again, just define De Morgan's laws carry over to these families of sets in a very natural way. The next operation is the Cartesian product. And here, what this means, elements of this set are going to be denoted as an ordered pair. So what it means to be an element of A times B means you have an ordered pair x and y such that x is in A and y is in B, right? And there's some other theorems in the text about taking products of unions and intersections and sort of swapping the two. That's a good exercise to look at. And the last thing in the section is defining what a function actually is. And this is the weird thing about this definition is that it is solely for sake of defining what a function is and explaining why we use the terminology that we do. So oftentimes you'll see this notation, f is a function from A to B, right? What this means, a way you can define what a function actually is saying that it is a subset of the Cartesian product such that for each x in A, there is a unique y in B such that the pair x and y is contained in F. And so this uniqueness is why we use the notation y equals f of x, right? If you try to define a function, you might be inclined to say, oh, it's something, you'll probably tend to use vague terms like, oh, it sends elements of one set to another. Really, this is a proper definition as far as definitions go, but it allows us to justify using this notation and the intuition that we have for it, right? It's not that the intuition is wrong, it's just not a definition, right? There's just really just pure math semantics that you could argue as not that important, but sometimes it is important to be correct. So that is it for this first lecture. And I'll see y'all in the next video.